Hi, my name is Fikruzzaman. Me and my team will present our systematic review and meta-analysis. We compare the effectiveness of machine learning predictive model versus traditional method in reducing injury among athletes in high contact sport. Here is the roadmap of today. We will begin with introduction and problem statement. Then our research question and objective. Next, we will discuss the method from eligibility to risk of bias. We will show the result, followed by discussion, recommendation, and finally, a concise conclusion. Machine learning is the transforming sport medicine. It helps turn complex data into the real-time injury risk insight. But sport injury are multifactorial. Traditional method often fail to capture their dynamic. AI has success in the other healthcare areas, but in the high contact sport injury, it underused. Most studies focus on the accuracy, but they lack transparency, validation, and real-world usefulness. Despite growing interest in machine learning in sport medicine, its impact is limited by key weaknesses. First, underrepresentation of complex injury, poor methodological evaluation, focus on prediction over prevention, lack of model transparency, and inconsistent terminology. This systematic review addresses this gap by synthesis current for research question. First, what are the current definition of artificial intelligence and the predominant AI method used in sport injury prediction? Number two, how accurate are these AI method in predicting injury occurrence? Number three, how effective are these methods in preventing sport injuries? Now, we go to our objective. First, identify current adoption and commonly used AI method in injury prediction and prevention. Number two, assess the accuracy of this method in predicting injury. And last, synthesize the evidence on advanced AI approach through a systematic review. Now, we go to the result. We register our protocol in Prospero and followed by PRISMA 2020 guidelines. The review used a structured and pre-specific systematic review. Apply the structured PICO framework to ensure focus and comparable evidence. First, involve athletes in high contact sport, for example, rugby, soccer. Number two, use machine learning model to monitor training load and predict injuries. Number three, compare ML method with traditional risk prediction approaches. Number four, report outcomes such as injury evidence, type, or recovery will exclude if they involve of non-contact sport or athlete in rehabilitation, lack machine learning intervention or predictive data, address non-sport related injuries, use retrospective or cross-sectional design, or where non-English publication without clear injury data or model application. This Sankey diagram illustrates our identification to screening process. We identify 2,217 records through database search on Scopus, PubMed, Web of Science, and Ovid. After automated duplication in EndNote, 526 duplicates were removed, leaving 1,691 unique title and abstract for initial screening. Dual review apply eligibility criteria, excluding 1,419 record and retrieving 201 full text paper for detailed assessments. For this slide, from the 201 full text article retrieved after title and abstract screening, a detailed review was conducted. At this stage, as a result, only 11 studies meet all eligibility criteria and form the final dataset for our synthesis. Our search strategy was broad, systematic, and fully documented. We searched PubMed, Web of Science, Scopus, and Ovid Medellin from inception to 10 January 2025. Using a structured PICO approach, we built search string that map population, intervention, comparator, and outcome element. Key terms include machine learning, high contact sport, injury predictive, injury prevention, athlete health and sport analytics. All search, both electronic and manual, were complete by 10 January 2025 and fully logged for transparency. This strategy allows us to capture both published and grey literature relevant to machine learning model in injury prevention in high contact sport. In addition to our main database search, we applied to extra layer to ensure that review was true and transparent. First, we conduct instructor hands searching, which include forward citation tracking of each include study and backward review of reference list. Second, we maintain transparent documentation, time-stamping every keyword string and Boolean search, achieving all PICO framework and database-specific adjustment, and exporting all search output with full metadata for audit purpose. This selection process follows a 6-step pipeline: exporting to EndNote, deduplication, review calibration, dual blinded screening, consensus on conflict, and Prisma compliance. We use control dual review process to ensure accuracy and completeness in data extraction. After removing duplicate with EndNote, all records were screened using Ryan and eligible study were entered into the pilot to electronic extraction form in Boolean logic check. We collect detailed information on athlete profile. At the study level, we record information such as a letter, year, setting, requirement method, eligibility criteria, machine learning technique, hardware use, training dose, supervision, and algorithm adaptation rules. To ensure equality, a second review independently verified 20% of the data, and any discrepancies over 5% were resolved through discussion before synthesis. We assess study quality through a structured dual review process, where two reviews independently evaluate each study, resolving any disagreement by consensus or with senior input. List of budget tools were matched to study design, which is ROB2 to RCT, Robbins for frequency experimental studies, and ROBBT add-on for behavioral trials. For this risk level, we are categorized as low, some concern, or high, and overall centrally was graded using the grade framework, considering bias, inconsistency, indirectness, impression, and publication bias. We combine the evidence using two approaches. First, the statistical track convert all study results into common measure like AUC or odds ratios, followed by meta-analysis that accounted for factors such as sport type, injury type, and small sample bias. Second, the narrative track was used when data could not be pulled, summarizing key terms like model, explainability, and practical usefulness. Now, we go to the result. The review covered a total of 3,179 athletes from 11 high contact sport studies. The average age was 23.7 years, and each group was followed for about 9 months, typically spanning a full competitive season. This figure confirms that evidence is based on young adult, elite level athletes, making the finding highly relevant for real-world sport performance and injury prevention. Across the 11 studies included in our review, prospective cohort design dominate 5 papers or 1.5 of the evidence-based track athlete forward through an entire season. 2 studies adopt quasi-experimental setup that mimic intervention. Geographically, the evidence is concentrated in a handful of Western nations. Australia lead the field with 4 of the 11 studies, just over 1/3 of the total, while Spain contribute to. The remaining 5 studies were single contribute from Belgium, the United States, Italy, and United Kingdom. In our systematic review, only 3 of the 10 studies explicitly report blinding the people who judged whether an injury had occurred. 7 studies document obtaining informed consent, but 3 did not mention it. Most athletes were enrolled through their club routine, precision medical, with only a few studies describing alternative requirement routes. Our first research question asks, how is AI defined and which algorithm dominate sport injury prediction today? The most commonly used artificial intelligence method in sport injury prediction fall into 4 categories. Interpretable model like decision tree, advanced learning methods such as random forest, support vector machine, and artificial neural net. Current AI methods show strong accuracy in predicting sport injuries across different contexts. For hamstring and lower limb injuries, smooth boost combined with ADT3 achieve high performance with AUC score reaching 0.837 for hamstring and 0.747 for lower extremity injuries. In football and soccer, models like logistic regression, decision tree, and SG Boost report AUC between 0.76 and 0.88. For youth and AFL players, SG Boost and ANNs perform well, reaching 85% precision and 82.9% accuracy in detecting injury risk. In professional baseball, particularly for UCL injuries, SVM and knife bias achieve 75% and 72% accuracy respectively. For the last research question, AI methods have shown meaningful potential in preventing sport injuries, not just predicting them. This model assists coaches and medical teams with decision support, helping them manage risk more effectively. They can identify high-risk athletes early in the season and monitor them continuously. Our review highlights both the potential and current limitation of machine learning in injury prevention. ML models outperform traditional methods by integrating complex factors such as training loads, injury history, and fatigue, and provide more accurate, real-time, individualized risk insight. We recommend using large and more reserved dataset, integrating wearable technology for real-time data, and fostering collaboration between data scientists, coaches, and medical staff. Model should minimize false positives to avoid unnecessary risks, prioritize interpretability through tools like Sharp or Decision Tree, and be tailored to specific sport position. In conclusion, machine learning models show clear advantages over traditional methods in predicting and potentially preventing injuries in high-contact sport. They offer higher accuracy, better integration of complex data, and real-time decision support. However, their full potential depends on improving model transparency, expanding dataset, and aligning tools with the real-world needs of coaches and athletes. This slide is the key studies and framework that inform our review, including Ayala et al. 2019 and Carey et al. 2018 on machine learning for injury prediction. Full citations are available on request and have been included in the writing report to ensure transparency and reproducibility. Thank you for your time and attention. We welcome any question, comment, and feedback on our filing method or future direction for applying machine learning in sport injury prevention.